Imagine trying to paint a portrait while looking through a wavy, distorted mirror. The results would be, well, quite misleading. Remote sensing data often starts a bit like that distorted mirror. You absolutely must correct remote sensing imagery before analysis because uncorrected data contains inherent errors and distortions that can lead to inaccurate measurements, flawed interpretations, and ultimately, incorrect decisions. These corrections ensure the data accurately represents the Earth's surface and phenomena, making it truly reliable for scientific study and practical applications. The why behind these crucial corrections stems from several fundamental factors impacting how remote sensing data is collected. First, atmospheric interference is a major culprit. As electromagnetic radiation travels from the sun to the Earth and then back to the sensor, it interacts with gases, aerosols, and water vapor in the atmosphere. This interaction can scatter, absorb, and refract the energy, altering the spectral signature of the surface features. Without atmospheric correction, a bright desert might appear darker, or a lush forest might seem less vibrant, simply due to atmospheric haze. Second, geometric distortions are always present. Think about the Earth's curvature, the sensor's viewing angle, the platform's altitude and velocity, and even the terrain's relief. All these elements can cause pixels to be misplaced or features to appear stretched or compressed. For instance, a mountain peak might be horizontally displaced in an image due to its elevation, a phenomenon known as topographic displacement. Rectifying these geometric inaccuracies is vital to ensure that every pixel is correctly positioned spatially, aligning with real-world coordinates. Third, radiometric distortions occur due to variations in sensor calibration, solar illumination angles, and even the sensor's internal noise. Different sensors might respond slightly differently to the same amount of energy, leading to inconsistencies. Also, the time of day or season can significantly impact the sun's angle, affecting how much light is reflected from the surface. Radiometric calibration standardizes these readings, allowing for consistent comparisons across different images, times, or sensors. Essentially, these corrections transform raw, sensor-specific signals into meaningful, comparable measurements of physical properties on the Earth's surface. So, how do we tackle these issues? The process involves several key steps. You start with radiometric correction, converting raw digital numbers into physically meaningful units like radiance or reflectance. Then comes atmospheric correction, which aims to remove the effects of the atmosphere, often by using atmospheric models or ground truth data. Finally, geometric correction, also known as georeferencing or orthorectification, precisely maps each image pixel to its correct geographical location on the Earth's surface. These steps ensure your data is clean and ready for advanced analysis like land cover classification, change detection, or environmental monitoring. An interesting concept to grasp here is orthorectification. This advanced geometric correction technique not only aligns imagery to a precise map coordinate system, but also removes distortions caused by terrain variations, creating a map-like image where features are shown in their true ground positions. This is critical for applications demanding high spatial accuracy, such as urban planning or infrastructure development. Without it, buildings might appear to lean away from the sensor, or roads could seem displaced on slopes. Another key term is ground truth, which refers to field measurements collected on site to validate or calibrate remote sensing data, providing a crucial real-world reference for these complex corrections. By meticulously applying these preprocessing steps, you transform raw, noisy, and distorted sensor outputs into accurate, scientifically sound, and spatially correct information. This rigorous approach ensures that any insights you derive, whether tracking deforestation, monitoring agricultural health, or mapping urban growth, are based on a faithful representation of reality. This foundational work empowers you to make confident, data-driven decisions that truly reflected the Earth's dynamic processes.